As we said in the previous slide, we are considering the standard deviation at 5 and mean at 1000. Basically, we are taking the first scenario where we had taken the 5 samples and the calculated standard deviation was 5, mean was 1000. So mean minus 1 times the standard deviation, which is 5, is going to be 1000 minus 5, so 995. Mean plus 1 times of standard deviation is going to be 1000 plus 5, so we get 1005. Similarly, mean minus 2 times of standard deviation, that is 1000 minus twice of 5, or 1000 minus 10 is 990, or mean plus 2 times the standard deviation is 1000 plus 10, or we get 1010. So this is the range for mean plus minus of 2 times standard deviation. Now at this juncture, let us introduce the customer and his expectations. We had seen earlier the specs were 995 minus 1005, because we had said that the specification would be 1000 plus minus of 5 ml. So that's how we had calculated 995 to 1005. Now if we fit these values of 995 and 1005 on this normal distribution, we see that it coincides with the mean plus minus of 1 times the standard deviation. These values. We also saw in the previous slide that mean plus minus 1 times of standard deviation will carry about 31% of the data. So it means in this first scenario, only 31% of the process output will be able to meet the customer requirements. Rest all will have to be either reworked or rejected. Now it starts making sense for the business, right? So in this case, where standard deviation is considered at 5, only 31% of the process output complies with the customer specifications of 995 to 1005. Remaining 69% is either less than 995 or more than 1005. Either way, it's not complying to the specifications. Now this is the advantage of Six Sigma as a metric. It provides a quantified view for the leaders and tells how much exactly is the worth of the process in front of the customers. It brings in specific focus, and we know that whenever the entire team is focused on a specific issue, we find solutions to our problems and we end up significantly improving our process. So let's say in this case, this focus has led to change, led to improvements, and now the variance in the water volume filled in bottles, it has come down to 1 standard deviation from the earlier 5. So what it means now is that 31% of this new process output will lie between mean, which is 1000, plus minus of 1 time the standard deviation, which is 1 now. So that is between 999 to 1001. So in comparison to the old process where 31% of the output was spread out between 995 to 1005, in the improved scenario, the same 31% is between 999 to 1001. Now thinking about the specifications, which was 995 to 1005, in this second case, in the improved scenario, if we try to fit the same specs on to this normal distribution, we see that it is at mean plus minus of 5 standard deviation, where actually 99.8% of the data lies. So in the improved process, almost all the products, that is 99.8% of the products, they lie within the customer specifications. Hence, definitely the process has become much more capable and the customer will be happy. For the business, because of the quantification, on one side, we know that okay, 99.8% of the products are meeting customer expectations. From the other point of view, we also know that only 0.2% of the output is what is not meeting customer expectations. So this predictability improves the confidence and trust on the process, and also helps to take an informed decision on how much is the need to further invest in terms of improvements and enhancements. Now let's relook at the first case. The specs are 995 and 1005. So on either side of the mean, which is 1000, producer has a tolerance of 5 ml in which all the products should lie. But in this case, due to higher variation or standard deviation of 5, only 31% of the process output is lying in this range. So obviously the biggest culprit in a process is the variation or standard deviation. Higher the standard deviation, higher is going to be the spread in the data, and hence the process capability is going to be lower. The process performance is going to be lower. So to evaluate the performance of a process, the question we ask is how many multiples of standard deviations we can fit in this absolute range of mean minus spec. In this case, we know standard deviation is 5, mean minus specification is also 5, so we can just fit one multiple of standard deviation in this range. And this multiple is what we know as the sigma level. And in this scenario, the sigma level is 1. And hence, we rank the process performance as low. And sigma level helps to get a ranked evaluation of the process performance or capability. Now let's look at the improved phase. The customer obviously will never change his expectations from the business. So the given specifications of 995 to 1005, that is always going to remain the same. Hence the absolute range, that is mean minus spec, that also will remain the same, that is 5. Now we know that the improvement has now reduced the standard deviation to 1 from earlier 5. And now we can fit 5 divided by 1, that is 5 standard deviations between the mean and the spec. So on the higher side, the spec is coinciding here on the normal distribution curve, mean is here. So 1005 minus 1000, that is the range 5, which has not changed. What has changed is the quantum of standard deviation. Earlier it was 5, and hence it was taking the entire space, and we were able to fit only one standard deviation in this same range. But now, because of the improvement, standard deviation has come down to 1. And hence in this range of 5, that is from 1000 to 1005, we can fit 5 multiples of the standard deviation 1. Which means what? Now the sigma level has increased to 5. And we know that in this range of mean plus minus of 5 times standard deviation, about 99.8% of the process output would be lying. That is 99.8% of the process output will meet the customer specifications. And hence we rank this process capability as very high. And the same approach can be used to arrive at a target if we decide to take the process to 6 sigma from the current 5. In this case, we know that the sigma level has to be 6 because that's the target that we have taken. Spec minus mean remains the same, and as per the formula that we have seen earlier, sigma level is nothing but spec minus mean divided by standard deviation. And in this case, the standard deviation has to be estimated, right? So this standard deviation is unknown. So 6 is equal to 5 divided by sigma. So sigma is equal to 5 by 6, and we get 0.83, which means to take the process to 6 sigma, we have to further reduce the standard deviation to 0.83 from the present 1.0.